we now draw attention to a very important distinction that needs to be made, and that is between accuracy and precision. Precision is a concept associated with the smallest measurement that can be reliably made. So for example, we know that a micrometer can reliably give measurements down to the 100th of a millimeter. The caliper, on the other hand, is reliable only to the 10th of a millimeter. So we say that measurements done with a micrometer are more precise than those done with a caliper. Accuracy, on the other hand, has to do more with how true the measurement is. And in this regard, it is quite possible for a micrometer, even though it's more precise than a caliper, if it is defective, to be less accurate. For example, if we measured the diameter of this coin, a Belizean 5-cent piece, with a micrometer and got a reading of 3.2.130 centimeters, we would know something is wrong, especially if you're familiar with this coin. The diameter of this coin is about 2 centimeters, so a measurement like this would definitely be erroneous. But note, the precision is fairly high. We are certain right down to the 100th of a millimeter. So we have a very precise measurement that is very inaccurate. Please note that I am giving a very extreme example here. If a device doesn't give accurate readings, it doesn't necessarily mean that it is defective. For any given device, the very design could very well limit how accurate it could be. What is important is that you understand that accuracy has to do with how true the measurement is. So the degree to which a device gives you a truer reading, that device is more accurate. Here we have an example that I hope will further illuminate the difference between accuracy and precision. Here we have two identical pencils, and let's assume that their true lengths are very, very close to 10.75 centimeters. Someone using this ruler would report the length of this pencil as being somewhere between 10.5 and 11 centimeters. Someone using this ruler would report the length of the pencil as being somewhere between 10.0 and 10.5 centimeters. In both cases, the measurement would have an uncertainty of half a centimeter. So both measurements would be equally precise. We could say that these are equally precise rulers. However, both measurements would not be equally accurate. This would be the more accurate measurement because the length of the pencil is between 10.5 and 11. Let's assume again that this is truly the length of the pencil. Well, this is wrong, right? The true length of the pencil does not lie in this interval. So again, we have two equally precise rulers, two equally precise measurements, but these measurements are not equally accurate. This, in this particular case, would be the more accurate measurement. Let's try and develop a slightly more formal definition of precision. Here we have two rulers, and let's assume that they are both equally accurate. If multiple measurements of the length of this pencil were made using this ruler, you would not expect all the recorded values to be equal, but you would expect that at most the values recorded would vary from, say, 6.0 to 6.5 centimeters. So you would expect all recorded values to lie in this range, and so the range of expected values would be half a centimeter. Using this ruler to make multiple measurements, and let's assume these pencils are identical, you would expect at most the recorded values to range between 6.2 and 6.3 centimeters. So notice that the values that would be recorded then, in this case, would have a smaller range. The variation of the recorded values would be less. And so, a more formal definition of precision is made in terms of the variation in the values that would be recorded. Note that there is some connection between the expected variation in the recorded values and the size of the smallest interval that can be reliably measured. Often educators use this target bullseye to help to explain the difference between accuracy and precision. In this model, this red dot represents the true value of what is being measured. So in this case, these little block stars, by the way, represent the various measurements made, and recorded. So note that there is not much variation amongst the measurements. So since the variation is small, we say that this represents precise measurement. And also, these values cluster around the true value. So this measurement is both accurate and precise. Of course, if we look at this case here, the variation in the measurements is also small, so this is still a precise measurement. But notice they cluster very far away from the true value. So this represents a measurement that is precise but not accurate. If we come over here, note now the variation in the recorded values is greater, but they still cluster around the true value. So here we have a measurement that is not so precise anymore, but still fairly accurate. They are clustering around the true value. Of course, over here, this measurement is neither precise nor accurate. There is great variation in the values recorded, and they cluster far from the true value. So I hope this helps to further elucidate the distinction between accuracy and precision. Elucidate. Nice word to look up and add to your vocabulary. So applying our bullseye target approach to these rulers, and let's assume these rulers are equally accurate, well, these would be the patterns we would get. Notice that with a ruler like this, with precision down only to the half a centimeter, well then you'd expect a fair amount of variation in recorded values, but those values should cluster around the true value of whatever is being measured. Over here, we see that the precision is down to a millimeter, which is a tenth of a centimeter, and so you'd expect the variation then to be less. Formally speaking, precision has to do with the variation of the measurements that would be obtained using a particular device. Let's now consider the precision of calculated values as opposed to recorded measurements. Here we have a rectangle, and the length is reported as being 14.72 centimeters. This means that whoever measured this length is sure of these digits except this 2. This 2 has been guessed at. Likewise here, whoever recorded this measurement is sure of the 8 and the 3, and the 6 was guessed at. Now what we want to do is calculate the area, and we need to decide how many significant figures we're going to use to report the result of our calculation. Since this digit here is unreliable, let's say for argument's sake that the true length of this rectangle could be anywhere between 14.70 centimeters and 14.80 centimeters. Likewise, since this 6 is unreliable, let's say that the width can be anywhere between 8.30 centimeters and 8.40 centimeters. Of course, this means that the area can be anywhere between 122.01 centimeters, that's what we get if we multiply these two numbers, and 124.32 centimeters squared. That's what we get if we multiply these two numbers here. So remember, it's squared and squared. I think I forgot to say square a moment ago. However, if we were to take the values we have, 14.72 and 8.36, and multiply those two values, notice we get 123.0592. So do this on your calculator and you'll see that this is what you'll get. Now, if this is going to be a value that you're going to report, should you report this number as it is here? Looking at the range of possible values for the area, we see that these two digits here don't vary. Where the variation begins is in this position. So that means that these two digits here we're pretty certain about these, but this digit here, we're not too sure about that. So if we're not sure about this digit, then these obviously have no significance. So if we're going to report this area, we should report this area as 123 centimeters squared. Whoever reads this would understand that these digits 1 and 2 are reliable, and that this digit 3 is somewhat unreliable. And that's how we interpret significant figures. We always say the rightmost significant figure is the only unreliable digit in a number. So there's a rule of thumb that we can use here, and it goes like this. Whenever you're going to multiply two numbers, or divide for that matter, look at the number of significant figures in each of the numbers you're going to use. Here we have 4 significant figures, and here we have 3 significant figures. Well, then when you multiply these two numbers, the final answer should have only 3 significant figures. In other words, you should, in this case, round off your answer to 3 significant figures. Notice you only do this if this is your final answer. If this result is just one step in a series of calculations, then you should keep as many of these digits here as you can until you reach your final answer that you're going to report. And then, when you reach that final answer, you consider exactly how many significant figures you need to report.